For this video, I'm going to walk you through section 2 here of this intro part for AP Chemistry. Again, a majority of this is a review of honors chemistry topics. So in this video, I'm only going to show you specific things that are different from honors or new things that you need to know here for AP. You still need to go back and look at the honors videos and the honors information and make sure you have a firm grasp on all those topics. So this would include writing reactions, predicting products, types of reactions, moles, problems with empirical molecular, stoichiometry, limiting reagent, and then even a little bit with solutions. So again, I'm only showing you here the stuff that is different from honors that we're kind of adding on here for AP, but you still are required to know that honors information. And if you need to go back and watch some of those videos and review that information, definitely do that. The first difference we see here in this section is when we get to synthesis reactions. So I'm not going through all the types of reactions. I'm not going to go through and talk about the basic synthesis reaction, so on. I'm only talking about here the stuff that's different that we did not talk about in honors. So for AP, you need to understand here that when a metallic oxide reacts with carbon dioxide, it's going to be a synthesis reaction. Even though it's two compounds reacting together here, it is a synthesis reaction and you always form a metallic carbonate. All right, so whatever your metallic oxide is, when it reacts with CO2, you're going to get that metal now being in the carbonate form, so CO3 compound. So this is something you have to watch out for. All right, if I have metallic oxide reacting with CO2, it's going to be a synthesis, and I'm going to get that metal, but now in the carbonate form. So this is something different, something you definitely need to know for AP. It can make problems a little bit easier to solve if you know, hey, look, when I have this metallic oxide reacting with CO2, I'm going to get a carbonate forming with the metal from the metallic oxide. So definitely pay attention to this difference. Another new synthesis reaction that you need to watch out for here in AP is when you have a metallic chloride, like in this case, potassium chloride, reacting with oxygen, you will form the metal chlorate. All right, so what we mean by a metallic chloride is we have a metal with chlorine reacting with oxygen gas, O2, and you get that metal, but then ClO3, a chlorate compound. So this is something you just have to watch for, and you have to know that's what happens when a metallic chloride reacts with oxygen gas. It's a synthesis reaction, and it's something you need to know in AP. Same thing here for decomposition reaction. I'm not going to go through the basic decomposition reaction. That's something from honors you can go back and look at, but it's kind of the reverse of what we saw here in the synthesis. If you have a carbonate would not decompose into the individual elements. A carbonate, a metallic carbonate, would break down into the metallic oxide plus carbon dioxide. So this is just something you need to know. If you have a carbonate and it's going to undergo a decomposition reaction, you're going to get the metallic oxide, so the metal in the carbonate with oxygen plus CO2 as your products. This is a decomposition reaction, but you don't get just individual elements here. It's the reverse of what we saw for that synthesis with the metallic carbonate reacting, the metallic oxide reacting with carbon dioxide to give you the carbonate. So this is just the reverse of that. And we also see the same thing here for the chlorate. If you have a metallic chlorate and it's going to undergo a decomposition reaction, it will break down into the metallic chloride plus oxygen. All right, it's the reverse of what we saw here for the synthesis. So in AP, this is something you need to watch out for. If all you have is a chlorate as your reactant and it's going to undergo a decomposition reaction, you get the metal with chlorine plus oxygen gas here. All right, so it's something you need to watch out for. I just want to point out here for double replacement reactions, we did these in honors, but you need to make sure you realize that you do need to use your solubility rules here to see if they actually happen. So you do need to know your solubility rules. And typically here for these double replacements, you'll have an aqueous solution reacting with an aqueous solution, and one of your products has to be a solid in order for the double replacement reaction to actually happen. You could get liquid water forming. That would be an example where the reaction happens as well. But typically here, if you're not getting a solid as a product, if they're both aqueous, then it won't happen. So you definitely need to know your solubility rules and make sure you get a solid forming here or liquid water in order for the double replacement to happen. And we did combustion reactions in honors as well. Just want to point out that if you ever see anything about a combustion reaction being incomplete, then that means you just get carbon monoxide, CO, and H2O as your products. Typically, for a combustion, you get CO2 and H2O, but if you ever see the word incomplete with the combustion, then it's just carbon monoxide and H2O. Again, this would have to be told to you, but if you don't see anything about incomplete, then you would just do CO2 and H2O as your products for a combustion. You obviously still need to be able to balance it and all that, but I just wanted to point out and reemphasize that the incomplete combustion is CO plus H2O in case you ever see it. We did molar mass in honors, but again, just want to show you here that in AP, we don't want to be rounding the molar masses. So the molar mass you get for an element off of the periodic table, you have to use that unrounded number here in your problem. And then when you total it up, you try to give your unrounded molar mass. And you have to use that unrounded molar mass in your problems when you're doing maybe Stoich problems, so on and so forth. So when you're doing molar mass in AP, don't round your masses from the periodic table, use the entire number. This is something you just got to get used to. It's different from what we allowed you to do in honors. Percent composition is a very easy topic that we did in honors as well. If you were trying to figure out the percent composition, you would just take the mass of the element over the mass of the entire thing, times it by 100. AP uses percent composition a lot in problems. They may not explicitly call it percent composition. They might just say what's the percent by mass of a particular element or something like that. The key is anytime you're trying to do that where you're trying to find the percent by mass or a percent composition, it's just take the mass of what you're looking at, put it over the mass of the entire thing, and times it by 100. This is something you don't want to blow off because you can see it kind of used in problems in some different ways. So just realize here when they're asking you for something like that, mass of whatever you're looking at over mass of the whole thing times 100. Empirical formula was another topic that we covered in honors. So you definitely need to know it and you need to know the steps. But I want to point out something here that might have been a little bit different from honors. So obviously you need to know the steps, you need to know how to do the problems. But it's this part right here about the whole numbers. We know, and we did examples like this, if you didn't get a whole number here when you divided all by the smallest, if you didn't have the whole numbers, you had to multiply them all by a number to make them whole numbers. We only looked at like 2 possibilities here in honors, so we need to kind of expand upon that, and that's what the next slide is going to show. In honors, we saw examples here where when you divide it all by the smallest, if you ended up getting a number like a 0.5, all right, you had to multiply all of your numbers by 2 to make them to make that a whole number. But even if it was just 1, you had to do it to all of them. And then we saw, well, what if it was like a 0.3 or a 0.6? We had to multiply them all by 3 to make them a whole number. And that's pretty much where we stopped. But you do got to watch here. If you would do this and get a 0.25, you would have to multiply them all by 4. I know that's very close here to the 0.3, so you really have to be careful. Make sure you're giving a bunch of decimals here and not rounding too crazily or anything like that. Round when you're supposed to. But on an old AP exam, there was actually an example where the problem came out to be a 0.2, and you had to multiply all the numbers by 5. All right. I haven't seen this in a while, but I just want you to be aware that technically you could get a 0.25 or a 0.20, and you might have to multiply by 4 or 5 respectively. So that's kind of a little bit different from what we saw in honors. I'm not saying these are very common, but in theory, when you're doing these empirical formula problems, you could get answers and need to multiply by those numbers. But obviously, you need to be able to do empirical formula problems here, just like we did in honors, but watch for these slight differences. In honors, we did do versions of empirical molecular problems that involved combustions. They were definitely the more fun, more challenging empirical molecular problems. And I just want to give you a little bit more background information here, and then I'll show you one, let you try one, because this is definitely an AP idea. We were kind of doing some AP level problems in honors, but we didn't really explain too much about what was going on here. So just from a lab perspective, realize basically what's happening is like they're taking a sample of the compound and they are combusting it in the presence of oxygen. And then that's how they're getting information here about how much CO2 and H2O are forming. And then that can help them figure out what the actual formula here is of a particular compound. So if you remember these problems, these are the problems where they would tell you an amount of a compound was combusted and you got some CO2, some H2O, and you had to figure out the grams of carbon, hydrogen, and oxygen, and then do your empirical problem to figure out the formula. So they would burn the sample here in the presence of oxygen, a combustion, and then what happens is the water gets absorbed by magnesium perchlorate, and then based on the beginning and ending masses of the magnesium perchlorate, they know how much water was given off, and then the sodium hydroxide here would absorb your CO2, and based on the beginning and ending masses here of your sodium hydroxide, you would know how much CO2 was formed in this combustion, and then you could do the problem. So I just wanted you to see this. I'm not saying this would be something you would have to explain or replicate, but I want you to understand kind of how they're doing this in order to, get this information and calculate these problems. Remember, your goal with these problems here is to figure out the amount of carbon, hydrogen, and oxygen present so that you could determine the formulas. And if you remember from honors, we said you were able to do this because of the law of conservation of mass. If you were getting, H2O forming, the H had to come from somewhere. Well, it had to come from your original compound. Same thing for the CO2. The CO2 that forms, the carbon had to come from somewhere. It came from your original compound. The oxygen, though, could have come from the air, so we can't look at the oxygen that way, but you could still figure it out. So these problems are basically using this idea of the law of conservation of mass in order to be able to do that. So let's look at one of these empirical molecular problems that's a combustion type. Here is the basic setup of one of these combustion examples. So you can see in this problem, it's saying that 10.68 grams of vitamin C is combusted. Vitamin C only has carbon, hydrogen, and oxygen in it. It gives you an amount of CO2 and H2O that form in this process. And again, they would figure this out based on the previous slide you saw how they would kind of do this here in the lab. They tell you the molar mass of the compound is 176.1 grams per mole, and we want to know the empirical molecular formula of the compound. So remember here, your goal with an empirical or molecular problem is you have to get the grams of each element in order to be able to convert them to moles. And right now, we have the grams of CO2 and the grams of H2O. So we need to be able to figure out the grams of each of the elements here. So if you remember back to honors, you would always start with the CO2, all right, the grams of CO2, and you want to figure out how much is just carbon. If you have 16.01 grams of CO2, how much of that is just carbon? All right, so this might look a little different setup from how we did it in honors using moles here, but it basically is exactly what we did. We're essentially just trying to figure out how much of that many grams of CO2 is just carbon. So we know the molar mass here of CO2, so there's that many grams for every 1 mole of CO2. We know for every 1 mole of CO2, there's just 1 carbon in it, so 1 mole of carbon. And then we know for every 1 mole of carbon, there's that many grams of carbon. So from that, we can figure out that there's 4.37 grams of carbon in that much CO2. So what this is saying is, in 16.01 grams of carbon dioxide, there's just 4.37 grams of it that's carbon. Obviously, the rest here would be oxygen. And I don't care about that oxygen because some of that oxygen could have come from the air, not from the vitamin C. So I only care about the carbon. All right. So I got the grams of carbon here. Essentially, this is like a percent comp. You're trying to figure out what amount here of that 16.01 grams is just the carbon. So it's like a percent comp. So only this much is the carbon. So in order to do an empirical problem, you need the grams of each of the elements. Well, now you got the grams of the carbon. And remember, this works because of the law of conservation of mass. Okay. The carbon that's in the CO2 had to come from your original sample. And then for these combustion problems, you always do the water next. So they told you how many grams of water you have, and it's basically the same idea here. The only difference is you're trying to figure out how much of the water is just hydrogen. Again, I don't care about the oxygen because it could have come from the air. So same idea. There's that many grams of water, molar mass of water for every 1 mole of water. For every 1 mole of water, though, there's 2 hydrogen. So there's 2 moles of hydrogen, all right, H2O. And then for every 1 mole of hydrogen, there's that many grams of hydrogen. So when you do your calculation, only 0.489 grams of hydrogen, okay, is making up 4.37 grams of water. So only this small amount is the hydrogen. The rest would be the oxygen, which we don't care about. So now you have the grams of carbon, the grams of hydrogen here. All right. You need the grams of each of the elements. So you got 2 of them. You still need the grams of the oxygen. Remember, you can't figure out the oxygen the same way we just did with the carbon and the hydrogen because the oxygen could have come from the air. So what you do here is you use the original amount that you started with to be able to figure this out. So if you total up, okay, the amounts of your carbon and hydrogen, this is the amount of the original compound that's carbon and hydrogen. So take the original compound, which is 10.68 grams, that would be the carbon, hydrogen, and oxygen. If you subtract away the amount that's just carbon and hydrogen, you're left with the amount of oxygen that must have been in the original compound. So remember, you're always going to need to figure out the oxygen this way, where you total them up and then subtract away from the original mass of the compound. So now you know the grams of each of the elements in the compound. You have the grams of carbon, grams of hydrogen, and grams of oxygen. So now you can do your normal empirical problem. You have the grams of each element, go to moles, all right, divide by the lowest, and then make sure you have whole numbers, and so on. You continue on doing your molecular problem then. So this was just kind of the first part of the problem that's different. And then once you get to the grams of each element, it's just a normal empirical molecular problem. So you need to be able to do these combustion examples. They appear in a bunch of different units here in AP. If you continue that problem and continue doing the normal empirical molecular problem, these are the answers here that you should get for that problem. So I definitely encourage you to make sure you can go through an entire empirical problem and continue on to the molecular to get those answers. But obviously you need to be able to do the entire combustion problem, and we're going to try another example here. Here is another example of one of these combustion problems. I strongly urge you right now to pause the video, get out some paper, make sure you can do this problem, and make sure you can get the answer that I'm going to show you on the next slide. So I will work through the entire problem for you so you can see maybe if you messed up where you went wrong, but definitely pause the video right now and try this problem. Hopefully this is the answer you got when you did this example, C8H4O3. So again, it's just like the previous example. Take your amount of CO2, figure out how much of that is just carbon. Take your amount of water, figure out how much of that is just hydrogen. Add both of them up, all right, get the total amount of carbon and hydrogen. Subtract that from the amount of the original compound to get the number of grams of just oxygen. And then it's a normal empirical problem. Go to moles for each, get your numbers, divide by the lowest. And in this case, we got a decimal here. They weren't close to a whole number, so we had to multiply them all by 3 to get our whole numbers that we used for our formula. And this example only said do the empirical formula, so that's where we stopped. Definitely make sure you can do these combustion examples. Another thing that's different here that we really start to see in this section relates to the AP exam itself. We really got to get good with being able to do the multiple choice with no calculators. On the AP exam, there is no calculators allowed on the multiple choice portion. So you can be expected here to do some basic math, including adding, subtracting, multiplying, dividing, and you need to be able to do that by hand. And a lot of times you can just use rounding, simplifying here to make some of your problems easier. So this definitely requires practice. It's something we need to work on throughout the course here, and you need to be able to do this. Sometimes you have to use logic to eliminate answers. So I'll show you two examples here and show you how I work through the problems, but each person is going to kind of be different here. How you work through it and do the math in your head might be a little bit different, but I just want you to see how you can do this without a calculator. And a lot of times they will use numbers that cancel nicely. And you'll see that as we kind of do a bunch of these problems and a bunch of these examples. So this is something you do see a lot of this with Stoich on the AP exam and other concepts as well, but you can really be expected to need to be able to do this math with no calculator. This is an example of an AP multiple choice practice problem here that you would need to be able to do without a calculator. Okay, so if you look here at the problem, you can see they're telling you have 8 grams of N2H4, and they gave you the molar mass of it in the parentheses here. They listed it as grams to the mole to the -1, just realizing that's the same thing as grams per mole. Sometimes they'll give you the molar masses. Sometimes you'll have to do it, calculate it. In these types of problems where you can't use a calculator, I would totally round the numbers on the periodic table and get a nice rounded molar mass. That makes total sense to do that here. You are allowed to round a little bit to see which answers make sense. Totally would round the molar masses and not use the numbers directly from the periodic table. So there's 92 grams of N2O4, a molar mass of that. They're mixed together and they're reacting according to the equation that's given. We want to know the maximum mass of H2O that can be produced. So they're giving me an amount of N2H4 and an amount of N2O4, and I want to know the amount of water that can form. Well, that's a limiting problem. You have an amount of each reactant, so you're doing a limiting problem here. So I'm going to set this up for you, show you how it would be set up. So you just pick one and start. So if I was doing this, you might have to write some work down here. And again, you're not being graded on the work, so you can kind of rush through it a little bit if you need to, but I strongly urge you to kind of still include labels and stuff so you're not messing this up. But you would have 8 grams of the N2H4, and they're telling you that there's 32 grams of that for every 1 mole. And then we know here that there's 2 moles of the N2H4 for every 4 moles of the water. Remember, we're trying to get to the water here. And they are specifically asking me about the maximum mass. So it makes sense to keep going. We know that for every 1 mole of water, if you did the molar mass of water, there'd be 18 grams. So people will say, okay, well, how do you do this without a calculator? Well, I look for some similarities here and see what I can do. So the first thing I notice here is that if I was multiplying across the top, I'd get 8 times 4. Well, that's 32. Well, if you notice, you're dividing by 32. So 8 times 4 being 32, 32 divided by 32, essentially that's all 1. So you don't even have to worry about the 8 times 4 divided by 32. The only thing that's left is 18 divided by 2 times 1. So 18 divided by 2, that's just 9. Okay, so right there you can see that sometimes like I said, sometimes you do some of the simple math and sometimes they cancel out. But that's how I go through and do the math here in this particular problem. Again, you might do it a little different, but seeing how somebody's working through the problem is definitely important here. But remember, you still got to do the other part here. So you have the 92 grams now of the N2O4. And according to the problem, there's 92 grams of that for every 1 mole. And then we know, according to the equation, there's 1 mole of the N2O4 for every 4 moles of water. Remember, this is where you get to kind of floor it, Harold. There's 18 grams of water for every 1 mole. So when I do the math here, again, immediately I can see 92, but then it would be divided by 92. Well, that's just 1. So that's all gone. And then it's just 4 times 18. All right, so that makes the math a little bit easier here. And 4 times 18. So in my head, I say, okay, well, what's 20 times 4? Well, 20 times 4 is 80 minus the difference. All right, there's 2 off of each of the 4. 2 times 4 is 8. So minus 8, it's 72. All right, so immediately this problem says, what's the mass of H2O that can be produced? Well, it's a limiting problem. It's the lower of the 2 amounts. So you would get the 9 grams here. All right, but you could be expected to do Stoich like this on the AP exam with no calculator. And you have to be able to use these little tricks, use these little simplifying examples, and be able to do that and get the correct answer. Sometimes, they'll give you the molar mass like you did here. Maybe they'll tell you it's, 32 grams. And then the amount they'll give you of it is like 3.2 grams. So it's like a tenth of it. And that makes your math a little bit easier as well. So you got to start to get used to doing these multiple choice problems without a calculator. And I have some more examples on my website for you to practice. You could definitely go through, and you got to get good with doing these without a calculator. Here's another example, multiple choice practice problem that you got to be able to do without your calculator. So it's telling you that you have hafnium metal heated in an atmosphere of chlorine gas, and the product of the reaction is found to contain 62.2% hafnium by mass and 37.4% chlorine by mass. And they want to know the empirical formula for this compound. Okay, so the first thing I do is I find hafnium on the periodic table. It's number 72, and it has a mass of about 178. So hafnium here is about 178, and then chlorine has a mass of about 35 grams, right? According to the problem here, the product that forms is about, again, this is, an about here, it's about a third. So if you can find the answer here that has about a third of the mass of the overall compound being chlorine, then you would have your answer. So I just want to show you a few here. So the first choice is HFCl. So if you total this up, it's 1 HF, 1 Cl, comes out to be a mass of about 213. Okay, so if you think about this, chlorine would make up, if it's just HFCl, there would be 35 grams of chlorine in that 213 grams. So in my head, I would say, well, what's 1/3 of 213? Because remember, according to the original problem, about a third of the mass has to be due to the chlorine. So if you generalize this, a third of 213 is about 70 grams. So that one doesn't work because there's only 35 grams of chlorine in that compound. So that choice is out. And this is how I would approach the rest of the choices here. Total up the mass of the compound, figure out about, how much of that is chlorine, and the one closest to a third would be the answer here. You could totally go about this a different way, but that's how I saw to do this problem, and that's what worked for me. So I guarantee you, and I strongly urge you to go through and do this without a calculator to make sure you can. But when you do this, the answer, the one that should get the chlorine being about a third, remember it should be a little more than a third according to the problem, is going to be choice C, the HFCl3. So I strongly urge you to work through the math here by hand and make sure you can get that answer.